Hello friends, I am Professor D.G. Trivedi, going to take your third lecture for paper 6502, Electronics, Digital Electronics especially, D2A and A2D conversions. This is lecture number 3. In lecture number 1 and 2, you have studied two type of network which can convert a digital information corresponding to analog output voltage. And these networks are resistive divider network and binary ladder network. These two type of network which can convert a digital information into corresponding analog output voltage. Now, how this circuit is converting and what are the additional blocks which is required for converting this D to A networks. So, here we are going to study 12.3 D to A converters. Either the resistive divider or a ladder can be used as a basis for digital to analog converter. So actually the digital information is translated into analog voltage by these two networks, but additional circuitry is required. So it is the resistive network that is actually translation from digital signal to analog voltage take place. There is, however, the need for additional circuitry to complete the design of D to A converter, and that we are going to study here. As an integral part of the D to A converter, there must be a register that can be used to store the digital information. We have studied the shift register in semester 4. There are four types of the shift register: serial in, serial out, serial in, parallel in, serial out, and parallel in, parallel out. This four type of the shift register which can be prepared from the flip flops, normally RS flip flop or a D flip flop. And these registers are utilized for temporary storing devices. So this register is also an integral part of D to A converter, because whatever digital information you are having, that information has to be stored somewhere and then after it is going to be converted. So the shift register of such kind of can be utilized in the form of RS flip flops. So this register could be any one of the many types discussed in the previous chapters. The simplest register is formed by use of RS flip-flop with one flip-flop per bit. We know that the basic RS flip-flop or RS flip-flop is 1 bit memory device. So if you are having a 4-bit information is there, then the 4 flip-flops are required. If you are having 8-bit information, digital information is there, then 8 flip-flops are required. So here we are going to discuss about the 4-bit digital to analog converter, and corresponding to that, for each bit there will be one flip-flop, that means 4 flip-flops will be there. There must also be a level amplifier between the register and resistive network to ensure that digital signals presented to the network are of the same level and are constant. So one more things, because we know that from the flip-flop output, when output is going to be high, it need not be constantly 5 volt. It can be anything from 2.4 volt to 3.9 volt. So output of all the flip-flop which is going to be high, that need not be the same voltage level. So the same voltage level has to be presented as D to A converter, that means the input of resistive network. When it is going to be high, it should be the constant voltage, whether it is going to be the VCC or it should be ground when it is going to be low, 0 volt. And for this, there is another important block is required, and that is called level amplifiers. Level amplifiers will be having a two type of the inputs. That means one input is coming from output of the flip-flop and another input is from the precision register, precision voltage source. This precision voltage source is a very accurate, a regulated power supply which will provide a, let us say, plus 10 volt. That means constantly plus 10 volt will be there as one of the input of this level amplifier. Another input is coming from the shift register or a flip flop. When the flip flop is set, the output of the flip flop is going to be high, and that means if the input is high to the shift level amplifier, then output of the level amplifier should be exactly plus 10 volt regulated is required. And when the flip flop output is going to be low, that means it can be between 0 to zero point 0.4 volt anything, but output of this level amplifier must be exactly 0 volt. That means level which is going to be presented at the input of the resistive network must be constant for all inputs, all bits. This is required. That's why this level amplifier is must be required. So this resistor could be any one of the many types of discussed in the previous chapter. The simplest resistor is formed by use of RS flip-flop with one flip-flop per bit. There must also be a level amplifier between the resistor and resistive network to ensure that the digital signals presented to the network are of the same levels and are constant. Finally, there must be some form of the gating on the input of the register such that flip-flop can be set with the proper information from the digital system. So, there is a gating circuit is also required at the inputs. So, this gating circuit will see that either the shift register will get the input properly, either the set conditions or a reset conditions. So, the flip flop can be set or reset. If S is equal to 1 and R is equal to 0, that is called set condition. That means the flip flop is going to be set and it will hold this output 1 for indefinite period of time. And when S is equal to 0, R is equal to 1, that means it will reset the flip flop, and for this the gating circuit is required. A complete D to A converter in block diagram is shown in a figure 12.13a. Let us expand this block diagram shown in a figure 12.13a by drawing a complete schematic circuit diagram for a 4-bit D to A converter as shown in a figure 12.13b. This is the block diagram of D to A converter. So, what is the first block diagram? It is input gates or gating circuit. That means digital inputs are going to be presented to this gating circuit or input gates. And output of the gates, this may be n bit input, digital input signals will be there. So, output of this one will be such that it will provide the each input to the n bit shift registers, and from the MSB to LSB the inputs are going to be provided to the shift register, and according to the set and reset condition the shift register which may made from the flip flop can be set or reset, and that input is going to be presented to one of the input of each level amplifiers. So there are n level amplifiers will be there for each bit, and each one will be having one of the input is a constant precision voltage source and another input is nothing but the output coming out from each flip flop. And output of the level amplifier is presented to the resistive divider network. That can be a resistive divided network or binary ladder network will be there, which will convert this digital input signal to corresponding analog output voltage VA, and this way D to A converter is working. This is a block diagram. This block diagram can be converted into the schematic circuit diagram of D to A converter 4-bit. So you can see that a bottom one is completely R to R ladder network is there. This is 2 to R, 2R to R, which is terminating at the ground. So this should be the LSB. And here on this side 2R, and in between the branch there is a R is going to be there. So this should be the MSB. Now prior to this resistive network and shift register, that is a flip flop, level amplifiers are there, and you can see that before this shift register or a flip-flop, there is a gating circuit is required. Here from the left hand side, you can see that LSB is going to be there. That means there are two AND gates, two 0 bar and two 0 are supposed to be the inputs. So if LSB is going to be high, that means 2 0 bar, 2 0, 2 raised to 0 is going to be high and 2 raised to 0 bar is going to be low, which gives the output of this one is going to be high. When read-in line is going to be high, that means both the input of this AND gate is going to be high and S become 1, R becomes 0, that will set the flip-flop and output of the flip-flop is going to be 1, that means the input to the level amplifier is going to be high. And here the precision voltage source which is providing a constant voltage, fixed voltage. So output of this one is a precise VCC voltage is going to be available to the LSB of resistive divider network or 4-bit ladder network, and this is going to be the LSB will be there. On the other hand, if the LSB is going to be low, that means 2 raised to 0 bit, this input is going to be low, but 2 raised to 0 bar, this input is going to be high, and when this read-in line is going to be high, R is going to be 1, S is going to be 0, the flip-flop is going to be reset and Q becomes 0 or low, that means output of this level amplifier is going to be low. So LSB to this binary ladder network is going to be low, which is going to be available. So the same thing is going to be happen to each of the bit of this 4-bit digital input D to A converter, and corresponding to that output voltage is going to be generated. You will recognize that the register network used is of the ladder type. These level amplifiers each have two inputs. One input is of plus 10 volt from the precision voltage source and other input is from the output of the flip-flops. The amplifiers work in such a way that when the input from the flip-flop is going to be high, output of the amplifier is going to be precise plus 10 volt. When the input from the flip-flop is going to be low, the output is again precise of 0 volt only. The 4 flip-flop forms the register necessary for storing the digital information. The flip-flop on the right represents the MSB and flip-flop on the left represents the LSB corresponding to the requirement of binary ladder network. MSB is going to be on the right and LSB is going to be on the left of this binary ladder network, and accordingly the digital input data should be provided. Each flip-flop is a simple RS latch and requires a positive level at the R or S input to set or reset it. So to set the flip-flop, S is equal to 1 is required, and to reset the flip-flop, R is equal to 1 is required. The gating scheme for entering the information into the register is straightforward and should be easy to understand. With this particular gating scheme, the flip-flop need not to be reset or set each time new information is entered. That means whatever the prior information is there, according to the new information, when read-in line is going to be high, the flip-flop, each flip-flop is going to be set or reset depending upon the output of AND gate. So with this particular gating scheme, the flip-flop need not to be reset or preset each time new information is going to be entered. When the read-in line goes high, only one of the two gates output connected to each flip-flop is going to be high, and the flip-flop is either set or it is going to be reset according to the digital inputs. Thus, the data are entered into the register each time the read-in or stop pulse is going to be occur or it is going to be high. Either D flip-flops could be used or RS flip-flops could be utilized for this shift register. Now, this is when one signal digital lines are going to be obtained. It is happening. When multiple signals are going to be available, then what to do? Then there are two methods. We can decode this digital information into analog output voltage. Quite often, it is necessary to decode more than one signal, for example, x and y coordinates for a floating board. So you know that sometimes there is a one channel line is going to be obtained for X channel and other digital information is for the Y channel will be there. To plot a graph, or if there is a three dimension X, Y, Z, three outputs will be there. For that, the one information is decoded for a X coordinate, another information is decoded for the Y coordinate, and third information is decoded for the Z coordinates, and that way the plotting is going to be possible. This is called multiple digital signals are coming and they should be decoded. And there are two different methods for decoding these multiple signals. The first and most obvious method is simply to use one D to A converter for each signal. This method, shown in a figure 12.14a, has the advantage that each signal to be decoded is held in the resistor and analog output voltage is then held fixed. So the first and foremost method is that for each channel, individual D to A converter, like previously we have studied, is utilized. And they will convert the digital information for X channel and then after it will be stored and held fixed there at the output. For another channel, another digital information will be obtained and it will be stored in a Y output, and the third digital information will be decoded and stored in the third D to A converter and stored in the Z output will be there. So the digital input lines are connected parallel to each converter. The proper converter is then selected for decoding the select line. So which decoder is activated, that is decided by this select lines. So this kind of method is called individual method or select line method, you can say that. That means digital information is provided in parallel to each D to A converter and select line selects one of this D to A converter and output accordingly will be stored into that particular D to A converter. The second method involves the use of only one to D to A converter and switching its output. This is called multiplexing, and such a system is shown in a figure 14.12.14b. The disadvantage here is that the analog output signal must be held between the sampling periods, and the output must therefore be equipped with the sample and hold amplifier. Another method is we can utilize the multiplexer. What is the multiplexer? One into the many. So here output of this one D to A converter is only utilized instead of so many D to A converter. Here only a common D to A converter is utilized and that converts the digital information into the analog voltage. And this information is going to be selected by multiplexer. And that output of this D to A converter is connected to the multiplexer input. And multiplexer is having many outputs like VA1, VA2, VA3, etc. etc. And it is between the two sampling time, it provides a different digital information, and corresponding to the different digital information, analog output voltage is going to be generated, and that analog output voltage is going to be stored at VA1, VA2, VA3, etc. etc. VAN, and digital information is there that can be decoded 1 to n multiplexer. So this method is known as a multiplexing method. The second method involves the use of one D to A converter and switching its output. This is called multiplexing. And such a system is shown in a figure 14.12 12.14b. The disadvantage here is that the analog output signal must be held between the sampling periods only. So, whatever the analog output voltage of D to A converter is obtained, that is remains fixed or for a temporary only during the sampling only. When the next digital information is there, the output is also going to be changed. So whatever this output is sampled, that has to be stored somewhere. So the sample and hold amplifier is required for each digital output. So this disadvantage here is that the analog output signal must be held between the sampling periods only, and its output must therefore be equipped with the sample and hold amplifier. You can see this. This is the first method A, right? Here there is a channel selector. Digital input lines are there. These digital input lines are connected in parallel to each D to A converter. This may be for the X, this may be for the Y, this may be for the Z, or there are n numbers they have shown here that this is a channel selector which is selecting either this D to A converter or this D to A converter or this D to A converter. When there is a information, one is going to be present, maybe 4-bit information is there or 8-bit information is there, that digital information is converted to corresponding analog output voltage which may be designated VA1, and this is going to be hold fixed here and it will be stored for desired period of time. Then when the next information is there, this D to A converter is inactive, but the next D to A converter may be active and that digital information is converted corresponding to the analog output voltage VA2 for the Y channel, and similarly for the Z channel, like this way. So by sampling digital information to each D to A converter, out of n digital D to A converter, only one of this D to A converter is active because of this channel selector, and that D to A converter gives the analog output voltage and that will be stored permanently. So this is a channel selector method. You can see that first method is a channel selector method is there. Now in a second method, that is multiplexing method, digital input lines are there that is given to D to A converter, but only one D to A converter is present. So instead of n number of D to A converter, here there is only one D to A converter is here. And this D to A converter converts the digital information which is coming in a sequence one by one into VA1, VA2, VA3, etc. etc. And this is a multiplexer which is having one input and many outputs. So when the first set of the digital information is there, the first line is going to be connected and output is going to be stored at VA1, or it is going to be sampled to VA1, and this will be has to be stored through sample and hold amplifier, and that will give you VA1 which is going to be stored for a long period of time. Then when the next set of the information is there, again it is going to be converted by same D to A converter. Again there is another VA2 is going to be obtained, and that is going to be steered to the output VA2, and that will be stored and hold at the output of sample and hold amplifier VA2. And this way, this method is known as a multiplexing method. So here the output is going to be stored, only output which is going to be available is only for the sampling time. It's not output is available for permanently, like here VA1, VA2, VA3, etc. So here the sampling and hold amplifiers are required in a multiplexing method for each channel. Sample and hold circuit. An operational amplifier connected as in figure 12.15a is unity gain non-inverting voltage amplifier. That is, output voltage V0 is equal to input voltage Vi. That's why it is called the output is not inverted. It remains to be the same. Op-amp is having two inputs, inverting inputs and non-inverting inputs. So, if the input is given to the non-inverting terminal, then and it is a unity gate, that means the feedback resistance is going to be 0, and hence output voltage V0 is equal to Vi will be there, and it is not going to be inverted, but this op-amp will provide a infinite input impedance. That is the advantage of this op-amp. Unity gain non-inverting voltage amplifier. Two such op-amps are used with a capacitor in figure 12.15b to form a sample and hold amplifier. We'll see how it works. When the switch is going to be closed, the capacitor charges to the D to A converter output voltage. When the switch is open, the capacitor holds the voltage level until the next sampling time. So, this is the unity gain non-inverting voltage amplifier. V0 is equal to Vi. Inputs is given, that means the output from the multiplexer VA1 may be given to the non-inverting amplifier terminal plus 3. So, this voltage output is going to be the same as the input. Now, when the switch is going to be closed, this output voltage is charging this capacitor. Capacitor is charging very fast because output impedance of the op-amp is almost 0 ideally, but it is very low. So, capacitor is charging very fast, and then after, when this switch is going to be open, it will hold this voltage across the plate of the capacitor. Capacitor remains charged because input impedance of the second op-amp is infinite, so it will not be discharged easily. So, it will hold that information for long period of time, and again it is slowly and slowly decaying because of a large input impedance of the second op-amp. But at that time, again the second sample is going to be available, and again it will charge this capacitor, and that way the charging is going to be very fast, discharging is very slow, and degrade of this voltage is almost not there. So that way the output voltage VA1 is going to be hold, and this kind of sample and hold circuit is required for each channel for multiplexer. The operational amplifier provides a large input impedance so as not to discharge the capacitor appreciably, and at the same time offers gain to drive external circuits. When the D to A converter is in use in conjunction with the multiplexer, the maximum rate at which the converter can operate must be considered. This is also important. That means whatever the sampling rate is there, how many times that sample has to be given, that depends upon the capacitor is going to be used. That means capacitor is going to be charging and discharging. Capacitor is holding that information. So, capacitor should be charged very fast and it should be discharged very slow. And before it is going to be degraded or before it is going to be discharged sufficiently, next sample has to be available. That means sampling rate should be very large is required. More and more sampling is going to be required, but it has to be synchronized with the op-amp as well as the multiplexer. So, when D to A converter is used in conjunction with the multiplexer, maximum rate at which the converter can operate must be considered. Each time data is shifted into the register, transient appear at the output of the converter. Sorry. This is due to mainly to the fact that each flip-flop has sufficient different rise and fall times. So each flip-flop is having different propagation delay times, and thus the settling time must be allowed between the time data is shifted into the register and time the analog voltage is to be read out. So whatever the digital information is here, which is going to be coming out of the flip flop, which each bit will be having a different propagation delay time, and hence you have to wait for the sampling time, settling time, and accordingly the sampling of the input signal should be provided. This settling time is the main factor to determine the maximum rate at which multiplexing the output. The worst case is when all bits are going to be changing, like 1000 to 0111. So here each bit is going to be changing. So it is having a different propagation time for each flip flop output, and hence you have to wait for more time. Naturally, the capacitors on the sample and hold amplifier are not capable of holding the voltage indefinitely. Therefore, sampling rate must be sufficient to ensure that this voltage do not decay appreciably between the samples, because the input impedance of the second op amp is also not actually in practice infinite. It is sufficiently large, it is high, but still because of that resistance the capacitor is going to be degraded, or it is going to be discharging, and the voltage across capacitor is decreasing. And before it is going to be decreased sufficiently, there should be a next sample or next input has to be appear, so that capacitors again start charging. The sample rate is a function of capacitor as well as the frequency of the analog signal, which is expected at the output of converter. At this point, you might be curious to know just how fast a signal must be sampled in order to preserve its integrity. Common sense leads to the conclusions that more often the signal is sampled, the less sample degrade between the samples. So, more and more times, often, if there is a digital information is to be sampled, degradation of the capacitor is less and less, and it will be hold that information for long period of time, and it is going to be constant. So, more sampling is required. On the other hand, if too few samples are taken, the signal degrades too much. The samples and hold capacitor discharge too much, and signal information is going to be lost. So, if the information is not coming often and often, the capacitor is discharging through the input impedance of the second op amp, and the signal information is going to be lost. We would like to reduce the sampling rate to the minimum necessary to extract all the necessary information from the signal. The solutions to these problems involves more than we have time for here, but the results are easy enough to apply. Solutions to these problems involves more than we have time for here, but the results are enough to apply. First, if the signal in question is sinusoidal, it is necessary to sample at only twice the signal frequency. So, what is important? If the signal in the question is sinusoidal, sine waves, then it is necessary to sample rate at only twice the signal frequency. For instance, if the signal is a 5 kHz sine wave, it must be sampled at the rate greater than or minimum equal to 10 kHz. In other words, a sample must be taken every 1 upon 10,000 seconds, or equal to 100 microseconds. The digital information has to be sampled to the capacitor. What if the waveform is not sinusoidal? Any waveform or any audio waveform may be the complex waveform of Fourier series, just like a summation of sine and cosine waves. Any waveform that is a periodic can be represented by the summation of sine and cosine terms, with each succeeding terms having a higher frequency. In this case, it will be necessary to sample at the rate equal to twice the highest frequency of the interest. So, In a Fourier sine series or cosine series, whatever the maximum highest frequency you desire, that is in the output information, double to that frequency, that should be the sampling rate is required. Thank you very much, friends.